Okay. You brought me candy. Awesome. No. Okay, so briefly administratively, I'm expecting there's project proposals in SmartSite. I know they're arriving. The important thing about those is that they are basically a contract between you and me, and I want to hear what you're actually proposing to do. Not just, I'm going to vaguely study this thing, but this is what I'm actually going to do. And we're happy to keep having a conversation about that, but I want you to make that a concrete proposal. I know I'm not the most quick grader in general, but I hope for most of you that sent me things as I requested a pre-proposal, I got back to you quickly. And I will also read these hopefully fairly quickly and get back to you on the formal proposals. But the pre-proposals were good, and I think everybody I've talked to has a pretty good idea of where they're going. Anybody have anything administrative? Okay, well what I'm hoping is today we're going to get through pretty much all of texturing. And so we started this last week, and just to very briefly go through some of the things this is basically what we're going to do. We'll talk about textures and texture filtering. We'll talk about a little bit about how this was implemented in some of the late SGI machines. We'll talk about caching, because that's very important. Probably won't have time to talk about prefetching. We will talk about compression, because that's also important. We talked about sort of what texturing was and why we use texturing and different kinds of textures and the fact that we can use textures for things that aren't just pictures. So this was this cool geometry images work that stored geometry in a texture. And so practically people use textures for all sorts of stuff. And they store crazy things in textures. It's just this is the place where you store global data. And graphics hardware is really good at doing texturing. Okay, so any questions on any of this before we move on? Okay, so first piece of new material here. This is from an excellent texture memo here, and for many, many years this was private, confidential within Pixar. They've actually released it at this point, so if you want to read some really insightful things about texture, this is a good place to go. In fact, people reference this paper all the time and never had read it. You'll find dozens and dozens of references to this paper, even though it was secret until fairly recently. So anyway, the interesting thing here is what Peachy pointed out was this idea of texture thrift here, that you can make textures as big or small as you want to. You can have as complicated or not complicated geometry as you want to. None of that matters in terms of the amount of texture that you actually use. Okay? The only thing that counts as far as what you actually use is the depth complexity of the scene, the number of textures per surface, and the number of fragments rendered. It doesn't say anything about the size of the textures. It doesn't say anything about the number of surfaces, how many objects you're doing. Basically what we're saying is, well, to render an entire scene where the whole scene is covered with some sort of surfaces, okay, the depth complexity is how many things you're going to render at each pixel, so how many fragments you're going to have at each pixel. Okay, so that's important. How many textures you're going to do on each surface. So that's, are you going to do one texture lookup per surface or 5 texture lookups per surface? Okay, and how many fragments you're going to do, and size of the image. Okay, how many pixels the image is. So what that means is that Pixar practically has these ginormous textures. They're really big and lots of them. But for any given picture that they draw, the amount of texture that actually goes into that picture is the same. Whether they have big textures, small textures, doesn't matter. Okay, what matters is that we're just going to take this amount of texture per pixel, and we're going to only draw this many pixels. Okay. So that's an interesting thing. So what that means is even though they have gigabytes and gigabytes of texture, the amount they actually use is finite and predictable. Okay, so we're going to talk a little bit more about this next week when we get to the signal processing part of this course a little bit more. So in theory, a pixel is a point. In practice, a pixel covers a finite area of the screen. Okay. Now, a gentleman named Alvy Ray Smith, really bright, like SIGGRAPH Lifetime Achievement Award winner. He's the guy that actually named Pixar. He's also a very, very nice man. He wrote a paper called A Pixel Is Not a Little Square. So, but today I'm approximating a pixel with a little square. But I want you to know that a pixel is not a little square in general. Okay. So what we really want to do is we have our image here. Okay. And what we want to do at any given pixel, which we are approximating as a little square for the purposes of this discussion, is sort of look at that square and see all the all the different geometry that contributes to that square, and somehow integrate over this entire region. Okay, this region that's a square might be bigger than a square. Okay, practically it might cover, you know, a nice Gaussian blur or something. I mean, it depends on the characteristics of your camera and your monitor, and sort of integrate all the contributions of all this geometry and put it together into one color per pixel. Okay, that's the right thing to do when we render. Practically, that's a hard thing to do. I mean, because you need infinite precision to be able to actually tell what's in there. Typically, we've been talking about scenarios where we only take one sample per, you know, we reach in and we just take the sample at the middle of the pixel, and that's the only color we get. So in that case, we'd get gray here. Okay? And we'll talk next week about how we might take multiple samples per pixel. But basically, what we need to do is integrate over this whole region. And this is going to be really relevant when we start to talk about texturing. Right? Because what we do when we texture is we rasterize this guy and we get a fragment. And again, for the purpose of this discussion, a fragment is a little square. Okay? So what we need to do is go over into the texture and somehow take the mapping of this pixel onto the texture, okay, which covers some sort of area. And what we want to do is integrate over that entire area and then take the result of that integral and bring it back and use that color. Okay? From a signal processing point of view, that's the right thing to do. All right? If we actually look at the picture here, okay, we have this square mapping onto this area. We need to integrate over that whole area, put all those colors together, all those samples we get out of the texture, and then bring back the result and use that color. Okay? Everybody better be super clear on that. Everybody, any questions about what I just showed here? Okay? That's the goal of what we're trying to do. We are trying to sample this texture properly so that we get the right color out of it. Okay. So one thing we can do is we can just go over and take the nearest point. Okay, we can say what we should be doing is taking the integral over this big thing. What we're going to do instead is we're going to come over here. We're going to find the place in texture space that is the closest to whatever point we're mapping here, and we're going to take the texture sample at that point and bring it back. Okay? So what's the advantage of this? Fast and easy, right? This is the cheapest, easiest, fastest thing that we can do. What's the disadvantage of this? Okay, this point is a point in texture space is a very poor approximation for the picture, for the region that we should be integrating over. Okay? So, but this is called point sampling, right? Makes sense. We are sampling one point from our texture, and that's all we're doing. Now, we'd like to do better than this, and what we're going to look at the first half of this lecture is ways that we can do better than this. Okay? So, what we're going to be interested in doing is texture filtering. And a little bit of technical terms here. We want to be able to sample this texture properly. Okay? We want to take samples from there that are going to properly represent what the function is, the continuous function this texture represents. So the signal processing term here is called the Nyquist limit. And when we sample here, it's going to go over there and sample from texture space. And we want to make sure that the signal frequency in the texture is no greater than half the sampling frequency. Otherwise, we have aliasing. And so let me show you a little picture of aliasing. Camera can move over here now. Here's the problem that we have. All right, let's say we have a nice function here that goes 1, 0, 1, 0, 1, 0, 1. Okay? So this is the texture space over here. So we can reconstruct a continuous function here in texture space. Okay? All right, and that's what our function's going to look like. Okay, so that's cool. So then the problem is, what happens, so if I sample this function at these points, okay, I can reconstruct this function. Okay, and there's nice signal processing ways to do this. That involve like a sync function, and there is a proper way to get this function out. Okay? Now, the problem is, so right now I'm sampling at the Nyquist limit. Okay? The signal frequency of the texture is this here, and it is no greater than half of the sampling frequency, right? I'm sampling 2 per wave, so I'm right at the Nyquist limit right now. Let's say I sample less than the Nyquist limit. Okay? So now I'm going to sample here, here, and here. Okay? So that's going to give me this function here. And then when I reconstruct that function, I'm going to get a function that looks like this. Okay? Now, this is a high frequency. This is a low frequency. I did the best I could with these 3 points, and I reconstructed these 3 points properly, but I am undersampling. Okay? I am sampling beyond under the Nyquist limit. I need to sample at least the Nyquist limit. Okay? So, the problem is I now have aliasing. And what is aliasing? Aliasing is when high frequencies appear as low frequencies. This is a high frequency here, but now that I undersampled, it appears as a lower frequency here. Okay? The other place, so this is sort of aliasing in space. This is spatial aliasing. You also see temporal aliasing. Okay, so when you watch a movie with a car that gets going or a helicopter that starts spinning its rotors, and you watch the wheels go, or you watch the rotor start spinning, and it looks like they start spinning backwards. Okay? You've probably all seen that. And the reason why is an aliasing problem. All right? The problem is that we have a wheel that's spinning here. Okay? And if we properly sample the wheel, okay, we can see that the wheel in this case is turning counterclockwise. Okay? But if we sample the wheel here, 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 and then here, okay, and we only look at these samples, okay, it looks like the wheel is instead turning clockwise. Okay? Yes?
So I noticed that also happens just with your eye and a normal wheel. So does that mean you can calculate the sampling frequency of your eye or your brain?
Do you really see that in your eye? Because I'd worry about your eyes if you did see that.
Way, I feel like I do see that.
Do other people see that?
Maybe it's just me.
These aren't just spinners?
Yeah.
Okay, it could be one of those cars. Okay, I don't think I've ever seen that with my eye. Has anybody else seen that with their eye? Do you see it going backwards with your eye?
Okay, I think it's just me then.
Sometimes. Okay.
It could be because of lights are 60 hertz.
So that the lights will impose some sampling limits, and yes, these are 60 hertz lights. Okay, so when we do this in a digital domain, we're doing it in a, these are clearly, they're clearly steps in time. My guess is your eye does a lot of smearing. It does essentially a lot of integration over time, right? You're sort of sampling over a long amount of time. I mean, it's tractable that that happens. I don't think I've ever felt that phenomenon on my own. But, I mean, it's exactly this phenomenon, right? So could you do the sampling frequency of your eye? So, I mean, a camera has an aperture, and so like it opens and closes and opens and closes. And, I mean, it gets a certain amount of time. I wonder if it would be an issue with your eye or if it would be an issue with, like, the fact your brain is, does your brain divide it up into chunks, into frames? Or does your brain sort of interpret it in a different way? I don't know. Okay, this is a good question, right? This is we will talk a little bit about the psychophysics of how you perceive things when we get to future lectures a little bit. And we'll look at like color space kind of things. So I know a little bit about that. I do not know how your eye processes this. Okay. So that's a good question. Okay. Okay. So we want proper sampling here. Okay, we want to sample at least 1 pixel for every texel, and so that means we want to do at most 1 texel for every pixel. And so the problem is, what happens if we have very detailed textures? Okay, we have big textures like this. Okay, and how do we sample this thing properly? We're doing it incorrectly, and we will get aliasing if we do point sampling. We are sampling this texture not densely enough, and we'll get aliasing as a result. And we'll see some pictures why that's the case. Okay? So this is motivating why we want to think about a different way to sample, because if we only do point samples, we are not sampling this densely enough to avoid aliasing. And aliasing is very jarring to our visual system. We want to avoid aliasing. Okay. So yeah, last year there was a PhD comic about this. Hopefully all you guys read this. It's a fantastic comic strip. I guess technically I went to grad school with this guy. But I never knew him. But he does good work. So anyway, I'm pretty sure it should be 4 hertz, but I would hate to be wrong. Okay. Anyway, here's what happens when you undersample. Okay, so this is nearest neighbor sampling. Okay? You notice over here, which is, we're going to learn about this particular technique here, but you look and you have sort of a fairly high frequency, sort of ridgy kind of thing here. Okay? Here, if you look at that band right there, it's much lower frequency. Okay? You look at this band here, it's much lower frequency than it should be. Okay? That's aliasing. That is high frequencies masquerading as low frequencies. Okay? So, this is very visually jarring. Okay? First, it looks wrong in a static image. Second, if we're moving, okay, if we're actually looking at this and like we're moving very slowly, extremely visually jarring. Okay? We don't like that at all. What mip mapping tries to do, and we're going to see this later, is basically blur it out. Okay? If you look over here, it's pretty gray back here. There's not a whole lot of signal. Okay? We're blurring it out. But it turns out that's a lot better for our visual system than the aliasing. Okay? We're much cooler with blurring than we are with the aliasing. Essentially what this is back here is just this random process of picking samples. You're going into a very dense grid of texture samples and only sampling every few of them. You're basically just Monte Carlo picking a bunch of different texture samples, and that's why it looks so bad. Okay, so flickering, bad. And so we're going to look at better ways to filter, okay, so that we can do a better job sampling in general. And so there's a couple different ways we can do this. Okay, there's a couple different things that we have to worry about. One is the problem of what happens when we minify. Okay, and that's the much more common way to do it, which is you have a big texture and you're undersampling it. So basically, every pixel maps onto an area larger than a texel. Okay, so that's almost always what you're going to get. This goes onto this big image over here. You are undersampling and you are liable to alias, and we want to do a better job of approximating the area under that than we are currently doing with just a point sample. Okay? Or you can magnify, and that's where a pixel maps to a little tiny thing that is smaller than a texel. So there's theory for that, and I'm not really so worried about that. What we're really interested in is magnification, and that's what people care about. Okay, so here's one way we can do it. This is kind of cool. We're going to go over here, and we're going to have some sort of rectangle that it covers. But what we're going to do is, even if this is a very large region here, okay, this might map to this big region here, instead of just taking the closest point, what we're going to do is we're going to take the closest 4 points. And we are going to blend their values together depending on where we are in there. So if we end up with a sample that's very, very close to this point, then we're going to weigh this point more heavily than those points. If we end up right between 4 points, then we're going to weigh them all equally and bring them all back. So instead of taking one sample, we're now taking 4 samples. Okay? Turns out this has a large impact on how things look. All right? So the left is sort of, the left is the big picture, and then we have a smaller picture over on the right, which is a close-up. So the middle one is nearest neighbor. And the right one is bilinear sampling. Okay, 4 closest texels, weigh them, and we'll see how the math works in a minute according to the actual sampling point. All right. So what's the difference between the two? What do you see? How would you characterize those two?
The one on the right has better color transitions.
Okay. Okay. Less blocky. Okay. It's going to be a little more blurred out. Okay, in general, like it does look a little bit more blurry. Okay, if you kind of squint your eyes a little bit, it'll probably look even blurrier. But here, point sampling will create significant aliasing and blocking kind of artifacts. It's much smoother over here at the cost of some blurring. Okay, so we're now, instead of just taking 1 point out of this region, we're taking 4 points out of that region, and visually this ends up looking much, much better. Okay. So it's still a pretty bad approximation overall. Okay, we have this giant region right here, okay, that covers this whole thing here, and now instead of just taking 1 point, we take 4 points. But we're still not taking into account the issue of what we'd really like is to map over a region that's roughly the same size as our projected pixel over here. Okay, and we're not doing that at all with a bilinear kind of sampling. So what we're going to do is sort of extend bilinear sampling, and we're going to use a data structure called a mipmap. And so this stands for multum im parvo, and it means many things in a small place, this MIP. this is certainly one of the top 2 or 3 SIGGRAPH papers ever to be referenced. Like if you look at the number of references to this paper, everybody under the sun references this paper, okay? Because it's really good work. So here's what we're going to do. We want a pixel to cover 1 texel, all right? So what we're going to do is we're going to look at the texture here, and we're going to represent the texture as a big, full resolution image, okay? And then maybe we're going to have a region in here that's very, very large. Okay, so when we map a pixel onto this, it's going to make a big region. So that's bad because we're only taking this little region here. So then what we're going to do is we're also going to have a pre-filtered version of this texture that's half the size, and a pre-filtered version that's half the size of that, and a pre-filtered version that's half the size of that. So we're going to take the original texture and make it in a whole bunch of different sizes. And then we're going to pick the size that is going to allow this projection here to be roughly the size of this square. Okay? And then we're going to have a good signal processing and kind of match between the size we're sampling and the size and the actual size of the filter kernel. And so that's going to help us match our Nyquist limit. It's going to alleviate these sort of aliasing problems. So the picture we're going to want here is this. All right? We're going to store a bunch of filtered versions here. Okay? Image pyramid of low pass filtered images. So we've already filtered the whole thing, and then our job is to figure out the level of this that gives us the best match so that our filter kernel is the same size as this little block of texels that we're actually sampling. Okay, so that's cool, and this is going to make things look actually better. The tricky bit here is how to figure out what level we're going to be at. Okay, so we want to pick something so that the size of the pixel that's projected onto the texel is going to be roughly the size of a texel. Okay, that's our goal from a signal processing point of view. Now, the nice part is you can do this all before your application even starts, right? You can compute this, and you can compute this in such a way that it's very efficiently done. So you might think, oh, look at all the extra storage that I'm going to have. Well, if you store your texture like red, green, blue, and you're cutting it by 2 at for every possible size, this is red, green, blue, this is red, green, blue, and so on, you notice that storing the entire map is 4/3 of the size of storing the original texture. The original texture takes R, G, and B, and everything else fits in this square right here. So that's good. Okay, so it doesn't actually take a lot of space. So the nice part about this is that we can compute the map in constant time. Okay, we know that we're going to sample. If we go back to our pyramid here, we might end up with, say, level 1.5. So the way that we're going to do it is we're going to do bilinear sampling here, 4 points, blend. We're going to do bilinear sampling here, 4 points in blend. And then we're going to do bilinear sampling between these 2 levels. So if it's actually at level 1.5, we'll take half the value of this and half the value of this. Okay? So it'll take us 8 samples. Okay? But it'll always take us 8 samples. Okay, we know we're never going to have to take more than 8 samples. So it's totally predictable, and you can build hardware to be able to do this very efficiently. So the way we're going to do it is we're going to have one level here, take our 4 points, blend, blend, blend. Same thing up here, blend, 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 and then you do a blend here. So this is 7 linear interpolations. All right, so it's going to take us, in this case, trilinear, 7 multiplies and 14 adds. Okay, so that's groovy. So what the tricky bit is finding D. All right? Finding D is sort of this level here. Okay, we can compute the texture addresses with S and T, but how do we actually find D? All right, so if we're between level 1 and 2, this is how we're going to do it. Okay, it'll take 2 bilinear things. It's really good. Turns out this works very nicely in a texture cache too, so we're going to be happy about that. The question is, how do we get D? All right, so everybody cool with everything so far? Any questions about how I got to this point? Okay, so what we want is to figure out when we take our pixel and we project it onto texture space, what is the area of this texture? We want the area of this, the area of this is 1, okay? We want to pick the texture such that the area of this is also pretty much 1. Okay, we don't want it to be too big, we don't want it to be too small. We want the right pre-filtered size of the texture. So our goal is to figure out what the mapping is from here to here, which seems kind of complicated, but it turns out to be relatively simple, which is cool. All All right? And so this is the way we're going to do it. We're going to use derivatives. All right? We're going to calculate the derivatives, and we're going to see how those are useful in a second. So once we have these derivatives, how do we figure out what the area is? But we'd like to be able to compute the derivative of how much does s change when we change x by 1. All right? So we figure that out by saying, okay, we take the value of s at this point. Okay, it's going to map over to a particular s here. And we take the value of s at this point, and it's going to map over here. Okay? So the derivative is s here minus s here. So it's a discrete derivative rather than like some sort of continuous derivative. Okay, but all it is as I change x by 1, how much does s change? Okay? As I change s by 1, how much does y change? As I change t by 1, how much does x change? So these are easy to compute. Okay. So if we walk back a lecture, we talked about rasterization. And one of the things we talked about was, can you rasterize more than one fragment at the same time? Okay? And we said, actually, what people generally do is they rasterize things in 2x2 quads. So when you send fragments down the pipeline, you're blasting out a 2x2 quad at every clock cycle. Okay? But it's always a 2x2 quad. This is the reason why you have 2x2 quads. Okay? Because if you rasterize this pixel, this pixel, this pixel, this pixel, and generate fragments for them at the same time, then you can easily calculate these derivatives. If all you rasterized was one pixel at a time, then you don't have access to your neighbors. If you don't have access to your neighbors, you can't easily calculate these derivatives. So modern graphics hardware always rasterizes 4 fragments at a time, and they walk down the pipeline together, and the reason they do that is so that we can compute these. It's easy to compute these derivatives if you're rasterizing 4 fragments at the same time. Okay? So that sort of closes the loop on the rasterization part. Okay. So then you're saying, okay, John, I see that you can calculate these derivatives, but how the heck are they useful? Okay? So remember, the goal is we're trying to find the area of that polygon over there. Okay? We want that area to be close to 1. And so we kind of have to hack this. So it's not a very good way to do it. Okay? But it's an easy way to do it from a texture point of view. And so the actual thing that we need to do is some sort of like matrix sort of operation right here, and we can calculate it. Practically what we end up doing is essentially do a bounding box here. Okay? ds dx, dt dx, it's saying what is this length and what is this length. Okay? And basically this diagonal and this diagonal, we're going to take the larger of those 2 diagonals, and we will approximate this pixel size as this square. Okay? And then we're going to say what the level is the square root of the area of that square. And that's going to give us these levels from 1, 2, 3, 4, and so on. Okay? So that is the right, that's going to give us D. MIP D is this level right here. Level 0, level 1, level 2, level 3. Okay? So they're proportional to the log of the number of pixels in there, which is, again, the right thing to do. Okay. So we're using this sort of a hackish kind of thing to figure out what the right area of a pixel is. Okay? But it's really easy given that we already have these derivatives now. We calculate the derivatives. It gives us the area of this pixel. And then we can use the area of the pixel to figure out where the right place is in this map pyramid. Okay. So when is this approximation really bad? Okay, to take the longest diagonal and say, I'm going to have a square with that as the diagonal. Okay? Okay, well, but if we had a really, if we had a really big one, it's still going to work out okay. You just sort of make a square out of it. Okay?
But like where the width is really small.
Okay, what's really bad is when you have a square that sort of maps like this, right? Okay, that would be bad. Because remember, what we're trying to do is we're trying to figure out the area of this is supposed to be close to the area of a pixel. And we're approximating the area of this with the area of this square. Okay? So the bad thing is that this square is very different than this here. So if you have sort of squarish kind of texel mappings, you're fine. If you have something that's very long and skinny or very tall and skinny, you're in bad shape. Okay, this is a very bad approximation. What will happen if you do that is you're going to get over blurring. Okay, you're going to go to higher level of the bitmap pyramid than you otherwise would like to. And as a consequence, it's going to be much more blurred than you otherwise might like. Okay, so what we want to do then is do something they call anisotropic filtering. So anisotropic meaning not the same in every direction. And so you want to approximate this sort of oblong-looking texel as several more squarish texels. So basically you do one bitmap here and one bitmap here, and that is a better mapping than doing the big square here. So you're taking more samples as a means to be able to get a better approximation of the pixel area. Right. So it's still being done on one pixel. You're essentially saying, instead of taking 8 samples for this pixel, I'll take 16 samples for this pixel, and I'll organize them in 2 bitmap chunks. Okay? So if you see your card advertising, oh, we do 2-to-1 anisotropic filtering, what that means is it's capable of looking at that and saying, this is a really oblong-looking texel. I will approximate that with n different squarish texels. And so your card might advertise that it's able to do that. Okay, why do you actually want to do that? You want to do that for text. It actually turns out to be really good for text. So let's see. I believe the top one is bitmapped. And if you look at sort of the second row of text, it's really kind of blurred out. Okay, we have over-blurred that. Our texels are sort of oblong. That's not so good. We over-blurred it. We can't read it, whereas it's much sharper on the bottom there. Okay?
But what are those artifacts in the...
These crummy ones here?
Yeah.
I don't know.
Oh.
It's my bad. I mean, I pulled these out of a presentation, and I'm sure there's some PDF stuff. Okay, but this does the most good with text.
So you're still mapping with an isotropic, or?
Yes. So you're doing, instead of doing, so this, if we mapped it, would be a big square, and we'd do 8 samples. We're saying instead we're going to do 16 samples and just mip-map that and mip-map that and sort of
do 2 mip-maps instead of 1.
So it costs twice as much. If you did 4-to-1 isotropic filtering, then you would do 32 taps.
So if you see 16x in isotropic filtering, that means you're doing 16 of these squares.
Your hardware could do that if it got a really, really oblong thing.
Okay.
Yes. Yes, that's a lot of samples.
So in order to make that decision, it just compares like DS and DT. They're like, this done is very big, then you know it's a kind of oblong big thing.
Right. So you look at these two things, and if they're very different, okay. So basically, it's this versus this, right? So if this is very small and this is very large, you might say, boy, this is going to be better off anisotropically filtered. Okay. So these are kind of old pictures here. So point sample, bilinear on the top left, on the top right, and trilinear on the bottom. So you can see that there's a lot. Well, there's kind of a noisy texture on the ground here, but it's still very, very noisy up there, and it would be highly aliased. And you'll see that when you trilinearly filter here, it's basically turned that sort of aliasing into blurring. And that's going to be much better on your visual system when things actually move. Are there other differences that you see? Do things look better, worse?
The trilinear looks really blurry, though.
Yeah, I was going to say the point sample looks the best.
It's like a camera autofocus almost.
Okay. So it used to be you could run games at, it would be faster if you turned off the sampling. At this point, I think trilinear sampling is well enough integrated where it probably doesn't make any speed difference anymore. Okay, I should get some more modern examples than this. Okay, so what do you actually have to do to make this work? Just to look at sort of the compute requirements here. One thing is you have to be able to do a divide per pixel, and we talked about why, doing the projection. But this turns out to be, at least in the core graphics pipeline, before you get to really complicated shading and lighting, one of the heaviest pieces of math that you need to be able to do. So there's a very dense computational part of the pipeline, right? That's a fair number of operations that you do for every texture lookup. So one thing we're going to hear about on Thursday, Matt Farr is going to come up and he's going to talk about Larrabee to some extent. I actually have I haven't looked at his abstract yet, but I will send that out to you guys. And so Intel has this new processor where just about everything's programmable. The thing that they left as non-programmable was texture filtering. They said, well, we're going to leave texture filtering in special purpose hardware because we can do this so efficiently in special purpose hardware. There's enough operations here where it doesn't make sense for us to move it to something general purpose. Okay, we can build this much faster filtering hardware in special purpose hardware. Okay. One of the other things that we have is the reason that we have to do all this filtering in the first place. If we go way back in our picture here, okay, why do we have to do all this filtering in the first place? The problem is that this texture is something that we specify in object coordinates, right? I specify like my head in object coordinates. It's got textures on it. It's all nice in object coordinates. And then we go do this projection so that the projection of this image space pixel is weird, okay? Some strange shape when it goes through essentially this projection, okay? And this is a consequence of the fact that we do texturing in object space. We define our texture coordinates in image space, okay, and we define our geometry. But when we actually do our texturing, we're doing it in object space. And so that means that this pixel, this little square, when we project it into image space, is going to have some sort of weird shape. And so we have to do all this filtering stuff. So that sort of raises the question of, hey, what happens if we decide that what we really want to do is really good sampling here, and we don't want to have to deal with all this filtering kind of stuff. And so if we actually did all of our texturing in the same space where we defined our texturing, okay, if we did all our texturing in object space, then everything's perfectly filtered right away, right? So I say, here's my geometry here, okay? And I say this is 0, 0, and this is 1, 1, and this is the patch that I am needing to to texture. And so then I can say, well, this is, all I have to do is take the top right of my my texture and then just filter that down, and it's perfectly filtered. I don't have any of these weird shapes or anything. So this is actually what Raise does. So the Pixar rendering pipeline. They do all of their texturing in object space as opposed to image space. And so everything's perfectly textured off the bat. Okay? You only have to do one sample per as opposed to doing 8 or more samples per. And so they did this primarily because it ended up really reducing the amount of texturing that they needed to be able to do. So it's kind of an advantage of that sort of pipeline. Okay. Here's another technique that we can use to do a better job of sampling. So part of the problem better job of filtering. Part of the problem with filtering in general is that it's really good at, of bitmap filtering, is that it's good at getting squares and it's not so good at getting, long, skinny kinds of things. So here's what we're going to do here. What we want to be able to do is integrate under this blue square here. Okay, we want to figure out what all the values are. We have a texture here that's all 1, so it's a pretty boring texture. But we want to integrate under this square here. So here's the way that we're going to do it. We're going to take this, this texture, and we're going to create what we call a summed area table here. And the summed area table is such that every number here is the sum of all the numbers to the left and below it. Okay? So 12 is the sum of this whole rectangle here. And 8 is the sum of this whole rectangle here, and so on. So you can pre-compute this if you want to, okay? Or you can do it on the fly. We talked about the scan operation earlier in class. This is just a scan operation, okay? Everything is the sum of everything to the left and below it. Okay, so that's pretty cool. And the way that we will figure out what the area is under a rectangle is we will take this value here, okay, this rectangle here, minus this rectangle here, minus this rectangle here, and then we subtracted this rectangle twice, so we need to add that back in. And that's going to give us the area under here. Okay? The nice part about this summed area tables is that this will handle any width or height, right? It doesn't have to be squarish like it does in MIP mapping. We could say, hey, we can make it arbitrarily skinny, and it's still going to do a good job. It's still going to give us the right rectangle. It's still pretty much restricted to being able to do rectangles, but at least we can do rectangles and not squares and do them correctly. Okay, this takes 16 accesses to be able to work. You basically do bilinear filtering here, 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 and here. And so that's 4 times 4 axes. So it takes twice as many accesses to work, but the results are good, and it does a much better job with anisotropy. Okay, other stuff. SGI has a structure called a clip map. So a map pyramid sort of goes like this. A clip map is for doing like the scene in, what's the movie? Fight Club. Fight Club at the beginning, they start like out in the universe, and they like zoom into somebody's hand, like cells and stuff. So it's like 20 orders of magnitude difference. Anybody check me on this? It's a great movie. Okay. So they don't have room to store the whole map pyramid, so it's basically a structure that goes like this and then just goes straight down. So they start clipping as they move through the pyramid, but they are able to store something that's very, very, very deep, so they can do sort of these fly-throughs. Google Earth would be good at something like this, right? You can start off out in outer space and zoom down to your backyard. Okay. RIP map, so that's a MIP map that you downsample not just in square dimensions, but also in rectangular dimensions. You can define textures using polynomial stub. You can use noise. There's lots of different things that people do with textures that are, interesting kinds of things. Okay, any questions on textures and filtering in general? Okay. So now we're going to talk just a little bit about how this might be mapped to graphics hardware, and we're going to look at the Reality Engine, which is a 1992 thing. So we will look at this machine in more detail in a couple of weeks, but so start 3 weeks, I guess. We'll start off with, we get this whole bunch of geometry, and it sort of gets dealt out to a bunch of geometry engines, and each one of those processes different pieces of geometry in parallel. And then we divide things up into screen space kind of work. And so we have triangles that come into these fragment generators. So the fragment generators are what has to do the rasterization. So it takes a triangle off this bus, and we have a bunch of these operating in parallel. And the texturing is actually done in the fragment generator. So we're going to take a look at that in a little bit of detail here. Okay? So what's going to happen is we have a triangle come in, we project it, we take the derivatives, and so on. And what that's going to generate is 8 addresses. Okay, so the addresses are for the 8 elements in the MIP-map pyramid, right? We have to do 8 samples for every MIP-map access. Okay, so we send the original address here, and this is going to break it up into 8 addresses, and then we're going to look up a texture in each one of these. Okay, so everybody's going to look up one of the 8 samples. We're going to bring the samples back together, filter them using the right coefficients, the blending coefficients, and then send the color back here. Okay, so we got a bunch of these guys here, and so we sort of have some sizes here. One thing that's really a minus about this particular technique is if we look here, we can see that there's 10 fragment generators here. Okay, and this is what it looks like inside of each one of these fragment generators. One of the real problems with the Reality Engine is that each one of those fragment generators had its own texture. Right? You had to have your entire copy of texture in your own fragment generator, which meant that if you have 5 or 10 or 20 fragment generators, you have to replicate all that texture 5 or 10 or 20 times. So it was a very expensive way to be able to do it. Okay, so here's a tricky little question. All right, we have a single address we send over here, and this does sort of the MIP-map operation and figures out what D is and what the things are we want to sample. Okay, how do we guarantee that if we have 8 addresses to do, they'll go to each of these 8 DRAMs? Okay? It would be pretty bad if we generated 8 addresses and they all went to the same DRAM. Right? That would be pretty crummy, because then it's going to be 8 times as slow. What we want to be able to do is somehow distribute the texture over these DRAMs so that we can always, any sample we do, will always generate 8 samples that will be in 8 different DRAMs. How do we do that? So we have a point here, okay, and we have okay, but that's not. I mean, remember how MIP mapping works. MIP mapping works by taking 2 by 2 at this level and 2 by 2 at this level, right?
So it would be every odd texture level would be on the first 4, the last 4. Okay, so this is half of it. So half of it is saying that we have texture levels 1, 2,
Okay, and they get smaller and smaller as we go up. Okay, so if we had odd texture levels and even texture levels, okay, then we're guaranteed that all the odd axes are here and all the even axes are here. So that's good.
And on the inside 4, you split up that 4 textures into each one of the 4 blocks. Yeah.
Okay, so this is our texture, and we say this is going to go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so any rectangle I draw, well, that's a bad one. Why don't we do this one? Okay, I'm going to take 4 samples. They're always going to be from 4 different DRAM banks. Okay, so what I've done is I've taken my texture and I divided it in 2 different ways. Very good, by the way. One is every odd and, well, everybody sort of has an address that is S, T, and D. Okay, so this is basically odd S, odd T, odd D, odd S, odd T, even D, odd S, even T, odd D, and so on.
It's 2 to the third.
That's 8. There's 8 of them. 8 is good.
Yep.
Right, I have 8 banks of DRAM. Okay, so this solves our problem, right? We can guarantee that if we break up our memory in this way, then we can always get 8 parallel axes there. And so we can always do these things in parallel. Okay, so that's pretty clever on SGI's part. Okay, so the next generation, they still had fragment generators. We'll talk about this again later on. Just to see what they did, they tried to reduce the replication more, and they did this by having a lot more communication. So this is just a crazy crossbar. 32 by 80 crossbar is a very complicated thing to be able to do. But you'll notice that they still have 8 pieces of texture memory in here. Right, and so that's to make sure that but now it'll address 4 different texture filters instead of just 1 like they did before. Okay, so there's 2 more topics we're going to cover today. One is caching and one is compression. So the issue with caching is, we've talked about how bandwidth is getting slower. And there's a real issue with, data bandwidth is getting slower from off-chip, so we want to reduce that as much as possible. Okay? It turns out there is a lot of coherence in our texture axes. And so it will work to have a cache. We're going to talk about how that's the case. The problem here is that bitmap axes have very small grains. You're doing like 1 word at a time. Okay, you're only accessing 1 word at a time from each of those 8 banks. DRAM wants a big access. It wants you to get a whole chunk of things at a time. DRAM isn't very good about just going to grab 1 word at a time. DRAM wants to grab a whole coalesced chunk of 16 things at a time or 32 things at a time. So we've got this real mismatch here. So first we're trying to solve the bandwidth problem. Second, we're trying to solve this granularity kind of problem. Okay? So caches hopefully are going to help with this, but we need to have a way when we cache where we go up and grab a chunk of things at a time instead of just 1 thing at a time. All right, so how are we going to deal with this memory access things? Well, 1 is caching, 2 is prefetching, and that'll help alleviate memory latency issues, and 3 is compression, and we'll look at that in 10 or 15 minutes. Okay. So one of the questions that you might start off with and say, what's the unique texel to fragment ratio? That basically says how much reuse do we actually get? Okay, so are we reusing the same texels over and over, or does every fragment has its own texel? All right, so if it turns out that every fragment ends up getting its own texel, then this ratio is going to be 1, and that would be bad. We couldn't cache very well. If it turns out this ratio is very, very small, then that's probably good for us, okay, because then we can cache. So again, these are really old scenes that we've seen before, but they are really old. But just to look at the unique texture to fragment ratio, scenes are very different. So you get a lot of reuse in Quake. Okay, Quake just ends up using the same textures tiled over and over. Whereas you get to Flight and QuickTime VR, these are using bitmap axes, so there's more axes per fragment. But there's not a lot of reuse. Right? If you think about QuickTime VR, it's just this big panorama. So pretty much you're not getting reuse out of that, at least not very much reuse. So different applications are going to vary by a substantial amount. Okay. So things we care about, what affects locality? So are you using the same textures over and over, or do you have big textures? Are you magnifying or are you minifying all the time? If you're magnifying, that's going to affect it. How much do you magnify? Level of detail bias. That means in OpenGL you can say, all right, take whatever D I calculate and kick it up by a notch or kick it down by a notch. Okay? If you kick it that direction, make a lower D, then it turns out that makes your textures look sharper at the expense of some aliasing. So you can sort of fudge it a little bit either way. Okay, so these are just things that will affect texture locality. So if we want to build a cache, how do we do it? Okay, so what sort of things do we really care about? So in a cache, we care about a couple things. One is we care about the size of blocks, and a block is how much you fetch from memory at a time. You would like to be able to fetch a big block that's bigger than a single word at a time because DRAM wants you to access a bunch of stuff at a time. It's much more efficient to access DRAM that way. So how big is a block? And how big is your cache? What's the working set of things that you actually use? And do you want to make your cache direct mapped or associative? And we're also going to talk just a little bit about how we do these in memory and do these and how it deals with rasterization order. But these are the same sort of CPU-ish architecture things that you think about when you're thinking about just a general purpose cache. So for the scenes that we saw, we can just sort of look. And again, these are very simple scenes. We know that there's much larger caches and more complicated caches today, but nobody's really done academic studies on this. But just to show how much cache space you need, what we're looking at here is the regular scene, okay, and the scene with all the textures blown up to be twice as big because you expect textures to grow from generation to generation. Again, this is pretty old data. What it says is, as my cache gets bigger, I do a better job, and it doesn't take a whole lot of cache to do a good job for me, right? You get up to 16 or 32 kilobytes, you're pretty much getting, I mean, that's a pretty small cache in general, but you're getting a lot of benefit out of that, okay? The blue and the yellow bars are sort of the theoretical minimum. That's with cold start only. So Flight has much larger textual to fragment ratio, but it still turns out that a relatively small cache is going to do you a lot of good. QuickTime VR, same thing. Again, a relatively small cache will do you a lot of good. Okay, so how do you actually lay out the cache? This is kind of a clever thing. Okay, so what we want is we want to eliminate this. We want to make sure when we go out to memory to get a cache block, we want to get a bunch of stuff. All right, so you might think, okay, that means if you think about the way that you lay out an image, you do a whole line and then you do the next line and the next line. And so if you're going to go get a line, you're going to get this big long line of stuff, and you're going to get the whole line at a time. And that doesn't make a lot of sense in an image. In an image, what you really want is you want to get a block. Okay, that's going to give you more locality. You're going to get 2D locality, not just 1D locality. So block is good. All right, so we're going to actually organize our whole thing in this 2D style. All right, first we're going to have texels here. Okay, we're going to have a block of maybe 4 by 4 texels. Okay, instead of a block of 16 by 1 texels. So when we go grab a block from memory, we're going to grab 4 texels at a time. So this all makes up a block. Okay, but we're going to, if we access this with S3 and T3, and we put these in the address bits here, okay, S3 and T3, we're going to be, so, all right, let me do another drawing here. Okay, if we have, what do we have? S in this direction and T in this direction. Okay, so the obvious way for us to map this particular pixel here is to say that the address of this pixel is T times S max plus S, right? And so that means that when we're addressing, we address like this. Okay? That doesn't give us very good locality. Now, if we look at how this actually maps onto address bits, our address is going to look like this. This is going to be S, and this is going to be T. Right? T is going to be all the high bits, and S is going to be all the low bits. Okay? So T, and that's how our address bits are going to work out. What we want is more 2D locality. So the way we're going to do that is we're going to divide up our address like this. We're going to take a chunk of S and T here, and we're going to sort of interleave them, where we have a little bit of S, and then a little bit of T, and then a little bit of S, and then a little bit of T. Okay? And that's going to give us much better 2D locality. Okay? Because these together are going to define a particular block. And these 4 together are going to define an entire cache size. Okay, so a series of blocks that's in our working set and so on. So this is sort of this texture blocking idea. It's a 6-dimensional organization where this is your address within a cache block or cache line. This is your address within the cache, and then this is your global address. Okay. The other thing that's really going to affect this is this issue of rasterization order. So again, we want 2D locality. We talked about building different kind of rasterizers. It turns out you don't really want to go in scan line order. You don't want to do an entire scan line at a time, because that's, again, only giving you 1D locality. What you really want to be able to do is do a block at a time in the rasterizer. Okay? And if you do this block and then this block and then this block, you're taking advantage of 2D locality. So if you rasterize your triangles in blocks and you get 2D locality out of a block, it turns out it really helps your texture bandwidth as well. Okay. So that's all a bunch of sort of theoretical stuff. This is how it really, really behaves. And so I think this is a great data visualization here. This is Ziad Hakura's paper. And we're looking at the picture over there. And we're looking at basically how many cache misses we have. So every fragment in this image is colored. If it never misses, then it's white. If it misses once, it's blue. If it misses twice, it's green. If it misses 3 times, it's red. And so we see if we do linear addressing, like the one I drew over there, we don't do any blocking and we don't do any tiled rasterization, we get a lot of misses. Okay? As we start blocking, we get fewer misses. As we start tiling, we get fewer misses. And as we block and tile, we get the fewest misses of all. Okay? This is, again, an old paper. And that's unfortunate because, again, nobody's really done more modern studies with more modern workloads. And that's really a shame. But it does show that tiled rasterization and block textures make a big difference for you. Okay, so in general what you want is reasonably small working sets will work for you, at least with old school caches. NVIDIA, ATI, and so on, they don't really talk about how big their caches are, right? They just never talk about that stuff. So it's sort of nobody really knows. They also, we were pretty sure they have 2 levels of cache. That was in the picture they showed a couple weeks ago, which is good to see. But you know, they don't really release details on this sort of thing. Okay? Now, we want to prevent, in general, direct mapped cache works pretty well for these things. It turns out associativity doesn't help you very much, with the possible impact of having a 2-way set associative cache so that we can have both odd and even levels of the map in the same cache at the same time. Okay? Blocking, tiling, good. And we're trying to, yeah. Okay, anybody have any questions about caching? Okay, spend the last 20 minutes talking about compression. Okay, so when we usually talk about compression in the CPU world, we're worried about lossless compression. Okay, we want to make sure that if we call gzip and then we call gunzip, we get back exactly what we wanted. Okay, our visual system is much more forgiving. Our visual system is willing to deal with the fact that, all right, well, we're willing to you know, cut some corners there. It's cool. We're all right with that. And so here's sort of what they thought about when they thought about doing some texture compression. They said, all right, we've got some sort of texture here, okay, and we're going to divide it all up into a 4x4 block. And here's the way we're going to deal with this. We're going to try to compress this entire block of textures at the same time and try to save, it ends up saving, well, a substantial amount. We'll see exactly how much. So if we have 32-bit, like RGB A textures in here, then it's going to take 32 bits per texel, and 32 bits per pixel. And if we compress it using DirectX texture compression, we get down to 4 bits per pixel. Okay, so it's an 8-to-1 compression scheme, but it's lossy. Okay, so we have a bunch of colors in here, and what we do is we take sort of the max color and the min color. Actually, we're going to write min color way down here. Okay, so this is the biggest color we can have, and this is the smallest color that we can have in the block. Okay, then what we're going to do is we're going to have a min value, a max value, and 2 values in between. Okay, and then we're going to code each texel in here, in this block, with one of these 4 values. Okay? And this value we're going to do with 565, meaning 5 bits for red, 6 bits for green, 5 bits for blue. Okay, why do we do 6 for green instead of 5 for green? We wanted to add up to 16. Why did we pick green? Yeah, our visual system, for no apparent reason, is better at doing green. It's important for us to. It's more important for us to see green than the other colors. Okay, so we have more dynamic range with green. Green is cool. So we encode it with 16 bits each of these here, and then we take intermediate values here. Okay, so normally, if you look at a particular texture and you're doing my shirt or something, okay, this is mostly blue. It's going to compress really well because you can pretty much say this is all blue. Let's say we do a checkerboard here. Okay, and we have white and black. Okay, how's that going to compress? That's going to compress great, right? Because some of these are going to be max and some of them are going to be min. If it turned out this is like 1/3 gray, that would be perfect too. Okay? Now, if it turns out you make this red and this blue and this green, it's going to compress very, very poorly. So there are some things that this compresses really, really well, and some things that it compresses really, really poorly. Okay? But overall, this is 8-to-1 compression, and this is very common. Right? We're trying to save texture bandwidth best we can. If it's a sort of natural-looking texture that doesn't vary a whole lot, this gets us an 8-to-1 win, which is really, really very good. Okay. So the last one I want to show you here, and it will take me like 15 minutes to go through, is a particular paper from Jacob Strom, who's at Ericsson, really nice guy, gave us all the slides. It's got the best paper award at Graphics Hardware. And so Jacob works on mobile phones. So he works for Ericsson. This work and its successors are actually making it into the standard for how people do texture compression on mobile phones. So anyway, it's very nice work. And so I want to walk through sort of the idea behind how you develop a texture compression scheme, because this is a pretty cool texture compression scheme. Okay. So their first scheme was called Pac-Man. And so what the paper is iPac-Man, which is this improved Pac-Man. So first we're going to go over what Pac-Man is, and then we'll talk about how they made it better. Okay. So the first thing is that they divide up the texture into 2 pieces. Okay. One of the pieces is what they call luminance, which is sort of the brightness of the color. And the second one is chrominance, which is actually which color it is. Okay? Turns out MPEG does that too. So if you're looking at a DVD, you're looking at, pretty much any compressed video, it's going to divide things up into luminance and chrominance. The reason is because we as people are more sensitive to luminance than we are as chrominance. In general, what we want to do is we want to have a higher resolution luminance and a lower resolution chrominance. It's a better use of our bandwidth than having those 2 things equal. Okay, so we're going to compress those things separately. And the way we're going to do it is we're going to have higher resolution luminance, lower resolution chrominance, have sort of a base color here, have that modulate the color, and that's going to come out to be a good use of our bits from our visual system's point of view. Okay, so then the question is, how do we actually do this modification? Okay, so we want the base color plus the luminance. How do we actually, when we say modify the luminance for each pixel in the block, how do we do that? So the way they're going to do that is a particular technique called vector quantization. So they're going to say, well, we're able we're going to modify it. We're going to give you a few choices as to how to modify it. Okay? We're going to have this table in there, and then you're just going to pick from the table the one that's closest to the way that you actually want to modify it. And the way they did this is they took a whole bunch of pictures. I believe this is actually Tomas's kid. He was used as the basis for this. Took a bunch of pictures, figured out what was going to give them the minimum error there. All right, so they did a lot of work to be able to make this work. It's all symmetrical, so how do we modify it? Well, you can modify it either by adding or subtracting. To make it cheaper, they had it, the bits that you could modify were equivalent on either side, so that was pretty cool. And so here's how we actually do it. Those 2 are the same. Okay, so when we actually encode a particular pixel, or a particular block, this is the way we're going to do it. So we've got a block here of 4x2 pixels. Sorry, 4x2 texels. How are we going to do that? So the first thing we're going to do is we're going to specify 4 bits of red, green, and blue, and that's going to give us a base color for the whole block. Okay? Then we're going to have 4 bits that tell us what out of the table we're going to end up using here. Okay, so 6 bits will do that. Okay, it'll pull out modifiers for those. Then every pixel has 2 bits that tell us which out of the table we're going to use. And what that's going to do is allow us to use different values out of this table to modify the base color and give us some pixels here. Okay? So I know this is all seeming a little bit complicated. So what they found was this wasn't quite good enough. And so this is Pac-Man, and we're going to see what they thought about when they went to iPac-Man. All right, so again, let's recap here. It's a scheme where we only have 32 bits to color 8 different texels here. Okay? We're going to use some of the bits to tell us the base color of the texels. We're going to pick a particular line out of the modifier table, and then that will give us 4 different modifier numbers we can use. And then each different texel gets 2 bits to say how it's going to use those modifiers. Okay. So it turned out it was even worse than DirectX texture compression in terms of the signal-to-noise ratio, and it's got some blocking kind of artifacts there. So you can definitely see some blocking in that picture there. It just doesn't have enough color resolution was the issue. So they said, all right, well, I'm doing 444 color. It's just too blocky in terms of the base color. So we'd like to be able to do that. So what they said is, well, we have a lot of spatial redundancy. There's a lot of locality in our images. Instead of coding 2x2, 2x4 blocks, we're going to code an entire 4x4 block at a time. And that's actually going to be the same as what DirectX did. Okay. So one thing they found out was that the base colors of 2 blocks that were next to each other turned out to be very close together. So over there on the right is some data about, okay, you take 2 blocks that are next to each other, how different are their base colors? Okay, turned out they're not very different in general. Okay, cool. So what we're going to do instead of saying we're going to do the left block with 444 and the right block with 444, okay, because we know that they're kind of close together, we're going to do the left block with 555 and the right block with just a delta. Okay, so this is going to give us more resolution on our color, and that's hopefully going to help us out with the banding problems that we saw before. Okay, so what happens if they're too much different? Okay, if they're too much different, we got a problem. If this one's red and this one's blue, we're not going to be able to do it with a delta. So if that's the case, then we have to go back to doing 444 for each block. Okay, cool. The problem with that is that we need an extra bit. So we need to say, are we in differential mode where we're using the deltas, or are we not? Okay, so that's going to take another bit, which is not so good for us. Okay, and so where do we get that bit from? And so the way we're going to do that is we're going to shrink our code book. Okay, so the code book's going to be smaller now. We're going to only make it 8 entries instead of 16. So that's actually going to save us 2 bits out of the table. And so then we're going to use that to encode whether we take 2 next to each other this way or 2 next to each other this way. Okay, so it turns out this is much better overall. Okay. It ends up being better than DirectX texture compression on the sort of test that they were going to do. It has a lot fewer banded artifacts. And so it's primarily because now we can use more bits to actually encode our base color, and that really helps us in the long run. Okay, everything cool with this. So it's, this is what's actually used in mobile phones these days. They actually have modified it a little bit more with some later stuff, but this has been submitted to the standards body. And so if you look at this sort of decode technique, how you actually decode this thing, it ends up being very, very simple, right? So it's simple math to be able to get the colors out of this. Okay, you're looking it up in this little tiny table, so it's just this little table you look into. The amount of math it takes to undecompress this is very, very simple. So as a result, you're able to decode this very quickly and get this nice big win in texture compression.
How much space was saved when you compress the image?
Okay. Yeah, let's go back to, so what are we up to here? So it's the same. I just want to see the whole picture here. Okay, so this is 32 bits, right, for 8 texels.
How much was each texel in bits?
So that would depend, right?
Okay.
I mean, what your input format was. So basically, it's 4 bits per texel. It's the same complexity as this. If your original texels were 8888, okay, or really it's just 888, but practically you need it to be a word width, then you're saving 8-to-1 compression. If your original texels were 565, then you're saving 4-to-1 compression. If you send in 3 floating point numbers, then you're saving 24-to-1 compression and so on. So it depends on what your input is. The output is 4 bits per texel.
In a mobile phone, do we care more about the bandwidth or the space to store something?
So That's a great question. All right, so I'm not an expert at like mobile graphics hardware, but number one thing is energy. Okay, that's what you really care about. You care about battery life, and that's sort of the biggest complaint people have with their phones. I'll tell you, for the life of me, I have no idea why people want to do like 3D graphics on a mobile phone. But I'm not a 13-year-old boy, so I don't get it. Right? Do any of you do 3D graphics with your phones? I'm seeing a lot of nods. Anybody? Okay, 3D graphics is huge. Right? People love like 3D, but the people are not in this room. So, I mean, I don't study this because I don't understand it. Okay. The reason you do compression here isn't for bandwidth. The reason you do compression is just because you need to flip fewer bits if you send fewer bits over. This is absolutely an energy concern. Everything they do in mobile phones is let's keep the energy down as low as possible. That's what they really care about. Cost is pretty important too, because you're used to paying $1,000 for a computer, but you expect to get your mobile phone for free. So they also need to make it small so that they can make it as cheap as possible, and that's probably the other big consideration. But in terms of this, the reason they're doing this is for energy. What the mobile phone guys say though is if you actually look at a phone, the pixels need to be, and you look at sort of the solid angle that comes out of your eye on a computer screen versus on your mobile phone. Okay, the mobile phone needs to be even higher resolution because it's usually pretty close to your eye. Like the pixels need to be really precise and have good color. So they really do care about quality a lot. They want to make sure it looks good because you can notice when there's artifacts because it's so close to your eye. Okay, well that's all I got for today. So Matt's coming on Thursday. Hopefully we'll have another great talk.